Sorry, so I'm not going to have this recorded. I just got off today. But look at this diagram at the top. You can see what I'm talking about. So you can see the signal for the clock. And down here we have three data waves. We got waveform A, waveform B, and waveform C. All those waveforms below the clock, they carry information. They carry zeros and ones. If you drop these dotted lines down that represent basically the pulse width, the bit time, then you can see that this is a 1, this is a 0, this is a 1. But down here, look at waveform B. You can see that 0 starts here, that's a 1. And instead of this being one big giant 1 right here, you can see the bit time defines that is actually two 1s in transition. And so they kind of got it grayed out over here on this. This is clock click number 7. And they got it grayed out so you can see that right here I got a 1, right here I got a 1, right here I got a 1. Now since I'm on this diagram and I'm also running out of time, let me just keep talking about this diagram, because if you look below here, you see something interesting. You see in the middle picture, you see a computer talking to a printer. A computer talking to a printer. And so basically if you know anything about old computers, they have something, you guys are familiar with the USB port, but old computers have something called the serial port. If you have an older computer, it has a really big kind of ugly looking plug that you need this big thick cable that you used to be able to plug a printer in with it. Now you use a USB cable. But that serial port basically was a line where you would send out information. It was basically just one line for data. If there's one line, that means you got to send out those bits bit by bit, kind of in single file. And so they're showing you this, that each one of these bits right here are sent out one at a time, bit by bit, in a serial fashion. And that was okay to do back in the day because when you print something, you don't really need it to happen really fast in most cases. If you go to the picture below, now what we have is it's kind of hard to see, but we have a microprocessor. This is a microprocessor chip right here. And this is inside of the computer now. We're inside of the computer. We have a microprocessor talking to memory over here. So we'll talk about memory probably next week. There's different kinds of memory. There's what we call RAM and ROM, and there's other kinds that we'll talk about, but RAM is the most important. And so I have a microprocessor talking to memory, and memory, just for right now, just think of it as a place. RAM is a place to temporarily store stuff. So I want to move these bits around, and I cannot do it in a single file. I can't do it bit by bit. That would be much too slow. You'd be waiting on days for days for anything for your computer to happen. So notice, instead of having one line, we have one line right here. This is serial data transfer between the computer and the printer. Notice I have 1, 2, 3, 4, 5, 6, 7. I have 8 lines right here, 8 connection points from the microprocessor to the memory. Now that number 8 is important because we're gonna define something called a byte. And we'll just for right now, a byte is equal to 8 bits. And typically, this is not true of PLCs, but it's true of computers. The smallest atomic piece of information you can manipulate in a computer, your cell phone, a microwave, is going to be a byte, 8 bits. And so this number 8 is important. That's not true of PLCs. With a PLC, you can actually address a bit, but we'll talk about that later. The point I'm making here is, hopefully you can see I'm sending 8 bits in a parallel way, and I'm sending 8 bits in the serial way. It's going to take 8 clicks of the clock. Let me say that again. It's going to take 8 times as long, 8 clicks of the clock, to send those bits in single file, bit by bit, than it would if I do it the way I have it down here. And here at the bottom, this is parallel data transfer. 1 click of the clock, and all those bits go across at one time. So parallel data transfer is way fast, in this case, 8 times faster than serial data transfer. And so you might ask yourself, well, why don't I transfer everything? Why don't we make everything parallel data transfer? Well, there's a trade-off. In engineering, there's a trade-off to everything. The advantage of serial data transfer is so simple. It's a lot less there's just one line. There's one single wire. So it's simple. The disadvantage is it's extremely slow. Now, by slow, we're talking microseconds, which, a microsecond to a human is fast, but a microsecond to your cell phone, or a microsecond, in a microsecond, it can do so many things. A microsecond is like a year to a computer. And so if that's to wait a microsecond to do so, that's a long time. So serial data transfer is simple but slow. Parallel, I need a lot more lines. In this case, 8 more lines. So it's super fast, but it's more complex. It's going to be more expensive. So there's a trade-offs. We'll talk about trade-offs all throughout the course. Okay, I feel like I'm talking real fast. Let me pause for a second and let me calm down because I'm still kind of hyped up from earlier this morning. Let me pause and calm. I'm gonna have to take my well, you don't want to know about that. Anybody have any questions? Let me pause for a second. Anybody have any questions or comments before we I guess we're getting winding down. We're gonna have to wind down in a second. Anybody have any questions or comments over anything I talked about? And then I want to say one more thing before I dismiss you about this. Questions or comments on any of this material?
So when we're like in my world, when we're looking at motors, we talk about pulse width modulation. Would that be the same thing?
Wait a minute, hold on. Let me turn. I can't hear you, so I don't know if that's you or me. I'm going to turn my volume up. Yeah, my volume is down. Okay, go ahead. Repeat your question.
So like when I'm in my world, when we talk about motors, we deal with pulse width modulation. Is that the same concept?
That's a little different. So pulse width modulation is used to control motors, speed up motors, slow motors down. They're used for stepper motors. So that pulse width, that's a really good question. Pulse width modulation is a little different than this, but it is used for control. They're the same in the sense that it's used for control, but not in the same way as a clock. What are you, by the way, just out of curiosity, what are you using? Are you in the servo class or something? How are you familiar with pulse width modulation?
We use it for stage motors, for winches, and
oh, you're my CCM guy.
Yeah.
Okay. Are you talking? Oh, is that Jacob? Oh,
yeah.
Okay. Yeah. Okay. Yeah, that's Jacob. That's a little bit different, but it is used for control. There is used for control, speeding up, slowing down. Here is more saying this is defining bits. This is called a timing diagram, and the other thing that these waveforms do is not only say how much of a data waveform is a bit, but also how fast things happen. You heard of overclocking a computer. So you're actually talking about the clock signal that controls everything inside of a digital device like a computer. And it's I was upset today because I went upstairs, the computer wasn't working. I came in last night, I was here at 10 p.m. hooking up stuff instead of taking care of I mean, it's been a mess. It worked perfectly. I got a student to check all that. So when technology works, it works perfectly. And I come in this morning and none of it's working. But if you had to think about, don't even think about a computer. Think about your car. A car is way simpler than a computer. You go out and I have an old car, so I don't have the key fob. I stick my key in the ignition. I got to just turn the key over and the motor starts, right? Well, if you really think about it, you guys are METs and MEs and all of that. You're mechanicals. I'm not. Think about how many things have to happen. Not just happen, but they have to happen at exactly the right time just for your engine to turn over. Everything, sparks have to go at the right time. Things have to happen at exactly. If something was just a little bit off, your car wouldn't start. Well, multiply that by 1,000,000. A computer is an extremely complicated device, and things got to happen, and they have to happen at exactly the right time. If you're just one bit off, the whole system shuts down. And so it's a wonder why that this stuff works anyway. It's just really amazing that this stuff works. So I can keep going on. I need to calm down. So I'm gonna dismiss you guys now. Oh wait, there's one last thing. I'm sorry. So when I come back on Wednesday, I actually want to do you got to do this on the quiz where you got to tell me how many ones and zeros are being sent back and forth. So I got a practice problem. You see it up on your what you call your canvas. But what you got to do, and we'll do this in class on Wednesday when we get back. I'll come back to this. But what you got to do, I'll give you a clock signal. I may or may not give you these lines. If I don't, what you'll do is you'll have a data signal below, a clock signal, and what you'll do is you'll drop these lines down, and that's going to tell you how many ones and zeros you have. Well, I actually want the time, the actual time. So to do that, you got to start with something. I either have to give you the time, the period, the bit time, but usually that's not what you have. When you buy a computer, they say your microprocessor is so many megahertz. Megahertz, you can tell I'm old. Gigahertz now, right? So processors are running at gigahertz speed. So you can put that into this equation and tell the bit time for your processor. So if you know the bit time, then you know if I have to send 8 bits, you can tell me exactly how long it's going to take to transfer those 8 bits from one point to another. Once I give you one more piece of information, I got to tell you, are we moving these bits in serial fashion? Is it serial data transfer? Are we moving these bits 8 bits at a time? Is it parallel data transfer? So that's what that example is about. I just want to kind of say that because on the quiz, I think next week, there's a calculation just like this. So I want to make, not that I'm teaching to the quiz, but I want to make sure that we go through this and you understand how it's done. Pretty simple calculation, but when you get a chance, look at your canvas and you'll see what I'm talking about. We'll take care of it next week. So guys, I tell you what, I'm over time. I'm sorry, apologize. Guys, have a great rest of the day, a good holiday, Martin Luther King Day. I'll see you on Wednesday. I'll stick around after class. I don't have anything going on. If anybody has any other questions or concerns, I'll stick around. I forgot to ask you to text me. So if you have that number saved, go ahead and do it. If not, don't worry about it for today. And I'll see you next time. I'll stick around, though. If anybody has questions, you can just let me know. Thank you.
Thank you. Take care.
You too.
Have a good weekend.
Thank you so much.
Have a good one, Professor.
Thank you, guys. Thank you. D. John, Peyton, thank you. Noah, Dan, thank you.